In the chem activity number 14 and the corresponding videos, we are going to look at the theoretical justification for the relative acidity and basicity of molecules. Our approach will be to look at the factors which affect the stability of a conjugate base. And in particular, we'll be looking at what's called the atom effect, which has to do with electronegativity, or the size of the atom that bears the negative charge. And we'll also look at how resonance can affect the stability of a negative charge. We turn our attention to teaching model number 1, which lays out the framework by which we're going to look at this. So for instance, if we compare two acids, HA and HB, we'll let both of them react with water to form the hydronium ion and the corresponding conjugate base. The premise is that in order to predict in a theoretical way which acid is going to be stronger, we don't focus on the neutral acid, HA and HB, but rather we look at the corresponding negatively charged conjugate bases. We focus on the negatively charged species because the negatively charged species will differ more in their energy, and therefore their stability will impact more the outcome of these reactions. The idea here is the more stable the product is, the more likely the reaction will occur in the forward direction. So essentially we're looking at, well, what will stabilize the negatively charged conjugate base? The more stable that negatively charged conjugate base, the less reactive that conjugate base is. Less of a tendency, in a sense, for that conjugate base to pick up a proton and reform the corresponding conjugate acid. So the more stable the negatively charged conjugate base, the stronger will be the conjugate acid. So all of our comparisons will be based on these sorts of premises. To begin with, let us compare a series of acids that involve elements that are found in the first row of the periodic table. So we have methane reacting with water, ammonia reacting with water, water reacting with water, and hydrogen fluoride reacting with water. All of them form the hydronium ion and the corresponding conjugate bases. The pKa's for these reactions are as such. Now, one of the first things that you're asked to do is to compare the relative stability of the various conjugate bases. Now, we can compare the relative stabilities by looking at the pKa's. The higher the pKa, the weaker the acid is, and therefore the less stable will be the conjugate base. So I hope you can see that the carbide at the top here would be highly unstable. And if it were to form, it would very quickly pick up a proton and reform the methane. Whereas by contrast, the fluoride here is actually relatively stable. This gives rise, in a sense, to a stronger acid. The fluoride forms, it sticks around longer, it has a less tendency of picking up a proton. Now we predicted this based on looking at the pKa's. And of course the key question number 1 asks us to list the conjugate bases in increasing order of stability. So it would look like this. The fluoride being the most stable, the carbide the least stable. But then the key question number 2 asks us to propose an explanation for this. So here's where we're going to turn to the atom effect. So in terms of comparing these conjugate bases, the negative charge is on the carbon, the nitrogen, the oxygen, and the fluorine. For some reason, having a negative charge on the fluorine is more stabilizing than a negative charge on a carbon. When we compare atoms of elements that are found in the same row of the periodic table, we are essentially comparing atoms of similar size. So the understanding is that for atoms of similar size, those atoms that have a higher electronegativity, and so that's represented by this chi symbol right here, the higher electronegativity gives rise to an increase in stability and note of the negative charge. I emphasize that because later we're going to be looking at stability of positive charges. And so it's important to realize higher electronegativity results in an increase in stability of the negative charge. We'll be making use of this idea quite a lot as we compare different sorts of acids. So that's one part of the atom effect. To introduce the next part of the atom effect, let's compare a different set of acids. In this case, we're comparing hydrofluoric acid, hydrochloric, hydrobromic, and hydroiodic acid. pKa's for this acid are like this. And we're also asked to list the conjugate bases in their relative order of stability. In this case, the hydrofluoric acid is actually the weaker acid, which suggests that the fluoride ion, although actually relatively stable, is not as stable as the iodide ion. So the relative order would look something like this. The iodide ion would be the most stable, the fluoride the least. Now you're also asked to compare the relative electronegativities. In this case, the fluoride is more electronegative than any of the others, yet somehow the iodide, which has the lowest electronegativity, is the most stable. So going down the periodic table, fluorine, the chlorine, the bromine, the iodine, you can't use electronegativity to explain the relative stability. Rather, you have to turn to ionic size. You may remember from first year that going down the periodic table, the size of atoms and the size of ions changes tremendously. The iodide ion is much bigger than, for instance, the fluoride ion. As it turns out, it's more stabilizing to have the negative charge distributed over a larger volume. We'll see this sort of theme in other cases as well. So the iodide is more stable because that negative charge is distributed over a greater volume or space. We can put this down in words for atoms of different size. So therefore, going down the periodic table, an increase in size means an increase in stability of the conjugate base. The more stable the conjugate base, the more tendency for the reaction to occur in the forward direction, and the stronger will be the conjugate acid. To summarize these ideas concerning the atom effect, across the periodic table, we know that it's the electronegativity that plays the important role. So an increase in electronegativity is equal to an increase in stability of the negative charge. Going down the periodic table, an increase in size results in an increase in stability of the negative charge. Now we compared carbon, nitrogen, oxygen, and fluorine across the periodic table, but you can also compare phosphorus, sulfur, and chlorine. And then down the periodic table, we compared fluorine, chlorine, bromine, and iodine, but you can also compare oxygen and sulfur, and nitrogen and phosphorus. Of course, the sulfide, the negatively 2 charged sulfur, would be more stable than the oxide. And in turn, phosphide, negative 3 charge, would be more stable than the negative 3 charged nitride. So we looked at one factor that can affect the stability of a negative charge. And again, that's referred to the atom effect, and all atoms have some kind of atom effect. It's whether or not it's a better atom effect or a good atom effect, if you will. The next factor that we're going to look at that can stabilize a negative charge has to do with resonance. Now, resonance does not exist in all cases. So in this case, we can say, oh, there is some stabilization by resonance, or there's not stabilization by resonance. Again, you can't say there's no atom effect. There's some kind of atom effect. It's just whether or not there's a better atom effect. So you've done a tutorial on resonance, and at the top structure we show full Lewis resonance structures, but on the bottom we're showing the bond line resonance structures, and of course we work more often with bond line structures. When you have an anionic carbon, hopefully now you're getting comfortable that there is indeed a lone pair of electrons. This lone pair of electrons is actually delocalized, and the negative charge sits on both the left-hand side carbon and on the right-hand side carbon. Perhaps you can appreciate then that the negative charge is not localized. It's not just concentrated on one carbon, but it's distributed over 2 carbons. That's a stabilizing situation. And therefore, any conjugate base that has some degree of resonance is to some degree more stabilized. Now we'll see that we can in a sense combine both the atom effect and resonance to talk about the overall stability of a negative charge in a conjugate base. Let's explore a little more deeply the concept of resonance and how it impacts the stability of a negatively charged conjugate base. In this key question number 6, I'm asking you to draw all the resonance structures that go with these structures or these anionic molecules that I've labeled 1, 2, and 3. So I encourage you to pause the video and explore the different resonance forms that exist. I do ask you to consider using the curved arrow notation to keep track of the electrons. So for the anion labeled number 1, there are no further resonance forms. Whereas for the anion number 2, there's indeed a resonance form, and hopefully you recognize this as an allelic lone pair. So there's one other resonance form that goes along with this negatively charged species. In terms of the anion label number 3, we can imagine a couple of resonance forms. So there's an allelic lone pair that will bring the negative charge onto that central carbon. And again, that negative charge is associated with a lone pair of electrons. So again, there's an allelic lone pair, and there's a third resonance form that we can draw. Now, how does this relate to the stability of conjugate bases? Well, let's consider then our next set of acids, which look like this. So I'm looking in the teaching model number 5, and I've labeled each of these conjugate acids as 1, 2, and 3. Now, the key question number 7 says, based on your answer to key question 6, and the fact that the relevant pKa's are 33, 43, and 50, complete the above table. Now, we've already talked about the fact that the conjugate base, number 3, has actually 3 important resonance forms. And we've also talked about the fact that resonance forms are stabilizing of a negative charge. So I would argue that conjugate base that has the most resonance forms would be the most stabilized, and therefore that would correspond to a lower pKa. So the relevant pKa's are like this: 50, 43, 33. You can see that stabilization by resonance has a tremendous effect on the stability of the conjugate base. We're only dealing with hydrocarbons, and yet the pKa goes from 50 down to 33 with having these additional resonance forms. And again, you may want to summarize that in the first case, that conjugate base has 0 resonance forms, and then 2 resonance forms, and then 3 resonance forms. Now, the key question number 8 asks you to construct an explanation for why the conjugate acid number 3 is more acidic. Here's a possible explanation that you could use. Note that I'm using some short form notations, but I'm also being very specific about my languaging, and I encourage you that you will do the same sort of thing. So I state here, the conjugate acid 3 is the most acidic because, although the atom effect is the same, and so I acknowledge that all of the conjugate bases have negative charge on carbon. So I do state here, although the atom effect is the same, the negative charge of conjugate base 3 is the most stabilized. And it's most stabilized by resonance, or we can also refer to that as electron delocalization. Now, there's another point here that I really would like you to take notice. I talk about the fact that the conjugate acid 3 is the most acidic, but I explain it in terms of the conjugate base 3. And I make the statement that it's the conjugate base 3 that's the most stabilized. A common mistake at first is for a student to make a comment like, conjugate acid 3 is the most acidic because it is the most stabilized. The word it there would actually refer to the conjugate acid. So we're saying something like conjugate acid 3 is the most acidic because it's more stabilized, which makes no sense. If something's stabilized, it isn't going to be more acidic. So it's very important that you specify what is it that's more stabilized. In this case, it's the conjugate base 3 that's more stabilized, and therefore its corresponding conjugate acid is more acidic.